I want to talk actually about two kind of related problems. So the first part is going to work with Susana Gomez, who's sitting where, yeah, Susana is over there. And the second part is going to work with Jose Carrillo, Risa Kvalani, who is a PhD student at Imperial, and Andres Lichting, who is in Heihen and Bonn. And there is a series of preprints and so on. OK, so I want to look at basically, well, 2.5 models, if you like. So this, so first, this so-called Dasais-Wansik model, which is basically a bunch of nonlinear oscillators that are coupled through their mean. Then I want to look at a model of, well, I refer to it as noisy Kuramoto oscillators. That one has to be a bit careful because people use the term Kuramoto oscillators to refer to different things. And also models for opinion formation. OK, so I used the term agents in the title mostly in reference to models of this form. So, OK, so we heard this very nice talk yesterday about different electoral districts and so on. And I don't think that anyone, of course, seriously believes that models of this form can actually model how people vote and so on, but yeah, still. And then, so there are lots of interesting topics that I won't really talk about. So one is adding actually colored noise. So replacing white noise in these equations with colored noise. This is quite interesting. You can also add memory. So like we heard the previous talk about the generalized lines of an equation. So you can play the same game with like weakly interacting generalized lines of an equations, and under the Markovian, well, quasi-Markovian approximation, you can more or less do the sort of an analysis quite similar to what I will present today. You can add inertia and so on and so forth. And of course, there's a vast literature on this topic. So this kind of there are the standard applications like plasma physics and astrophysics and so on. There are more modern applications to the social sciences. The two kind of intriguing, if you like, applications that I'm sort of interested in are first models for systemic risk. So there is some work by Garnet, Papanikolaou, and collaborators where they look at equations of this form as models for systemic risk. And then there is, of course, a lot of literature on models for opinion formation that are based on dynamics of this form, both noisy and without noise. Okay. Right, so let me start by discussing about the first part then. So where I have this sort of quite standard model, and then the additional feature is that rather than assuming that I have only two or sort of a finite number of local minima in my potential, I actually have a sort of infinitely many of them, if you like. So I look at potentials of this form. So I decompose the confining potential into a large-scale part plus an oscillatory part. But I'm assuming that the oscillatory part is actually modulated by the large-scale variable. And first, I want to pass to the mean-field limit. This is well known, so there's nothing really new there. And then I want to look at the number structure and structure of stationary states. So if I pass to the limit as n tends to infinity, so then what we obtain is a nonlinear type Fokker-Planck equation for the limit of the empirical measure, the so-called McKean-Vlasov equation. And the point that the fact that it is nonlinear and non-local means that there can exist more than one stationary states. Okay, and I want to investigate the sort of number of stationary states as a function of the parameters in the problem. Okay, so the kind of typical examples of sort of two-scale potentials that I want to consider in the first part of the talk are things like this. So you have like this basic sort of two-scale Landau potential, if you want to call it, and then you superimpose periodic fluctuations. Now the scaling here is not sort of, I mean, I don't need the fluctuations to be so strong, right? I was too lazy to produce a better figure. And then you can think of situations where the dependence between the macro variable, if you like, and the micro variable is sort of multiplicative. Okay, so that's here somehow the confining potential is actually modulated. I mean, so I have so it's I refer to this type of potentials as non-separable potentials or multiplicative fluctuations. And in fact, this complicates things a bit because you can see that here I can have this kind of very flat behavior close to the origin. And in fact, for a potential of this form, I need to sort of cut the fluctuations. So I don't want them to grow as x goes to infinity. Right. So okay. So now, of course, we know if I fix the number of agents or particles, then we know everything about this problem. So it has a nice gradient structure. I can write down the potential or Hamiltonian. Since I'm assuming that V increases sufficiently fast at infinity, I have a nice unique invariant measure, which is a Gibbs measure. I can prove exponentially fast convergence to equilibrium and all these things. And I can also pass to the limit as n tends to infinity. And this is a problem that is, again, very well understood. So like the first few slides that I'm trying to introduce the problem, I could have given this talk in 83. I mean, in 83, I was 7 years old, so most probably I wouldn't have been able to give this talk. Yeah, I mean, that's somehow. There was already sufficient information in the early 80s so that you could have presented these slides. So formally, of course, you can easily, so with this kind of quadratic interaction, I mean quadratic interaction at the level of the potential, right? So a Curie-Weiss, if you like, interaction. Then I can pass to the limit in a quite explicit, to the mean field limit in a quite explicit way, because I can invoke some sort of a law of large numbers. So this long time, I mean, this average here, it's reasonable to expect that it converges to the expectation with respect to some appropriate probability measure. Or if you like, I write down the solution to the n-particle Fokker-Planck equation as a product of one-particle distribution functions. And then if I assume that I have a similar structure for the initial conditions, I can pass to the limit. And then I obtain this kind of nonlinear and non-local SD. So I'm a kin SD. And it's nonlinear and non-local because the coefficients, in fact, in the equation depend on the law of the process. So the corresponding Fokker-Planck equation then is written here. So it's usually called the Makin-Vlasov equation. And even though it's nonlinear and non-local, I have this kind of quadratic nonlinearity here. And I also have a non-local term since what actually appears in the equation is the first moment. I still have a lot of nice structure. It is a gradient flow with respect to the free energy, assuming that you interpret gradient flows the right way. And I have the entropic term here. I have the internal energy, if you like. I have the interaction potential and the interaction energy. And I know quite a bit about properties of solutions to this equation. So if I go back to the finite dimensional problem, then as I mentioned, there are no issues as to whether there exists more than one invariant measures. Since I'm assuming that my potential is confining, I can write down a formula for the corresponding Gibbs measure, and I can prove exponentially fast convergence to equilibrium and so on. Now, for the limiting equation, I can, the situation is not so clear because what I need to do is to write down the stationary Fokker-Planck equation, which is written here, and then I need to count the number of solutions to this equation. And it is not true, in fact, that when V, so in the case where V is non-convex, which is the case that I consider here, that only one solution to this equation exists. Now, so this is a good sort of starting point, if you like, for introducing what I actually want to talk about. Because now, if we look at the stationary Fokker-Planck equation, we can sort of make a guess on how the invariant measures to the limiting dynamics should look like. If I treat the first moment as a parameter, then I can introduce an effective potential that involves V plus x squared over 2 minus m, where m is the moment, times x. And I can, in fact, write down a whole one-parameter family of invariant measures. So in principle, there can be more invariant measures, and then they have this nice functional form, where z is the partition function, and where I need to make sure that m is indeed the first moment. Okay, so I have this so-called self-consistency equation, which is telling me that first moment is first moment. Okay. So I compute the first moment using this formula, and then this has to be equal to m. So this defines a nonlinear map, or a nonlinear sort of transcendental equation that enables me to count the number of solutions, okay, the number of stationary states. So the number of solutions to this equation determines the number of invariant measures that I have for my limiting dynamics. And in fact, I can also compute the critical temperature at which the number of stationary states might change, so by basically differentiating this formula. OK, so then if I look at the standard Landau potential without any kind of two-scale fluctuations, then the situation that I have is this. So depending on the slope, so here I'm plotting just the first moment and then also this nonlinear map R. And the number of times that these two curves cross gives me precisely the number of invariant measures. So m equals 0, so the magnetization, if you like, or the order parameter being equal to 0, is always a solution to my self-consistency equation, which means that E2 minus beta v plus theta x squared over 2, so with m equals 0, is always a stationary state. But then if I'm at sufficiently low temperatures, then two more, well, symmetric solutions emerge, so corresponding to non-zero values for the order parameter. And I have the standard sort of piece-fruit bifurcation. So my at sufficiently low temperatures, the uniform, so the state corresponding to zero magnetization becomes unstable, and then I have these two new solutions.
Can one actually prove that there are no other solutions?
Yes, yes.
Than the one from the Gibbs measures?
Yes. So this for this problem that I'm presenting so far, this was already proved in the paper by Dawson. So this 1983 paper.
There are only the equilibrium measures that one finds.
Yes. So you can, I mean, you still have this gradient structure and detailed balance and so on. So it's clear that for this particular problem, you only have Gibbs measures. But I mean, but no, you can prove it. And then you can also prove that you go from 1 to 3 solutions. OK? And in fact, this has been proved in a sort of more general setting for a family of problems that sort of include the one that I have presented so far by Tamura in recent work. By Tugo in recent work. But for the particular case of the Landau potential, this was already rigorously proved in the early 80s. In fact, in this paper by Dawson, he has a very nice proof where he obtains an equation of a system of equations for the stationary moments, and then he's using like diamagnetic inequalities and so on to count the number of solutions. Okay, so this is known. Right. So here's then how the free energy looks like, and as a function of the order parameter and of the inverse temperature, and then you can play all sorts of games. So you can add a small linear drift, and then of course the piece-fruit bifurcation breaks, and then you have sort of this discontinuity there and so on. Okay, so all this is well understood. What I want to do now is to sort of go through the same exercise, if you like, so to count the number of stationary states for this kind of dynamics. But in the case where I have small-scale fluctuations. Now, from these results by Tugo and earlier results by Tamura and Dawson and so on, we know that the number of branches in the bifurcation diagram is related to the number of local minima, or if you like, metastable states. So in particular, if I have a potential like this, if I take epsilon sufficiently small, and if I send the temperature to 0, so I would expect some sort of freezing, right? So I should expect that there will be infinitely many branches in this bifurcation diagram. So this is the sort of thing that I want to investigate. And we start by looking at locally periodic potentials, because in this case, we know how to also send epsilon to 0. I mean, we can do sort of homogenization theory, and we can pass to the limit. So now I have two parameters to play with. So I have epsilon, and I want to send epsilon to 0. And then I have the number of particles, and I want to send the number of particles to infinity. And let's see what we get. So if I fix the number of particles, then I can certainly send epsilon to 0. And this is sort of a well-known result. And recently with Andrew Duncan, where's Andrew? Hi. So with Andrew, we looked at this in sort of for an arbitrary number of small scales. So what you get then is this kind of dynamics. So I have decomposed my confining potential into the large-scale part plus the fluctuating part. And then I get this kind of reversible dynamics. So it's important to note that as I send epsilon to 0, so the dynamics remains is always reversible with respect to sort of the right Gibbs measure. So I have a diffusion tensor M that I can compute in the standard way. So I have to solve a Poisson equation of the unit torus, and then compute an appropriate integral. The drift term here is modified by adding this kind of, I don't know how to refer to it, like a local free energy or something. So I integrate the fluctuating part of the potential over its unit cell. So I'm assuming that the period is 1, just for simplicity. And then I take the gradient of the logarithm of this. Okay. And in fact, so if you like, the dynamics is modified in 2 ways. First, because the actual drift term is modified by, or rather, the actual effective potential is modified. Then I have the divergence of the diffusion matrix, as I should have it, and then everything is multiplied by m. And now, so in the previous talk, there was this question about Ito versus Stratonovich. So if you want to actually combine, yes.
What is M?
So I'll show you the formula for this. Okay, but it's a symmetric positive definite diffusion sort of tensor. But I'll show you the formula for this.
This result does not depend on the mean field character, right?
I haven't sent 10 to infinity yet. Okay, so this is finite dimensional. Now, so we heard about Ito versus Stratonovich in the previous talk. And if you want to combine the divergence of the diffusion matrix M with the temperature, well, with the noise term here, then this leads to the so-called Klimontovitz interpretation of this. Oops, okay. Nothing's broken. That's good. Yeah. Oh. Okay, thank you. Thanks. Okay, in fact, this started working. It wasn't working before. Now it's working. Good. So, okay, so then you get this so-called Klimontovitz interpretation of the stochastic integral. So if you do the Riemann-Sam discretization, if you like, then you have to actually compute the integrand at the right endpoint as opposed to the left endpoint or the middle. And of course, in like the chemical physics literature and so on, it is a known result that sort of the definition of the stochastic integral that is compatible with thermodynamics in the sense that for this dynamics now you get the right, I mean, it is reversible with respect to the correct Gibbs measure, is the Klimontovitz interpretation, or kinetic interpretation, in fact. Right, and here's the formula for the diffusion tensor. So you have to solve an elliptic PD on the unit torus, and then you have to calculate this integral. Right, so now if so once I have sent epsilon to 0, then I can send n to infinity. And this order of taking the limits is actually can be made rigorous because the sort of early work on mean field limits for interacting diffusions, for example, this paper by Hoyslager from 84, they do include the case where you have multiplicative noise. Okay, so you can actually pass to the limit. And then you have to check that you have the right growth conditions and so on. But this order is actually not a problem. Now, if you first want to send n to infinity and then epsilon to 0, we know how to do it formally, but we're not sure yet how to do it rigorously. So we have been trying with, well, I can tell you what we have been trying, but probably after the talk, at the end of the talk. Now, so what I want to then know is whether the 2 limits commute. And it's certainly the case, well, one would expect that the 2 limits, so homogenization and mean field limit, commute over finite time intervals. But this does not provide me with sufficient information on whether the 2 limits lead to the same kind of phase transitions. Okay? So in particular, if I fix epsilon, I take epsilon to be small but finite, then it's certainly the case that the structure of the bifurcation diagrams can be completely different. So for example, if I just take a quadratic potential and then I perturb it by adding small-scale fluctuations, for all finite values of epsilon, there exists a sort of critical temperature, if you like, below which I actually have phase transitions, right? Because this is not a convex potential. And in fact, if I send beta to infinity, so I mean the inverse temperature to infinity, and I also send epsilon to 0, I would expect that in this combined limit, I would actually end up with infinitely many branches. Okay. On the other hand, if I actually first send epsilon to 0, then the homogenized potential, it's easy to check, is basically just a multiple of x squared over 2. So then there is a unique invariant measure because everything is Gaussian and convex and so on. So this is actually, I think, a quite extreme case of sort of non-commutativity, that you can go from having no phase transitions to having like infinitely many branches in the bifurcation diagram. Right, so let me then present some numerical experiments. So I started like 10 minutes late, I guess, so I don't know how much time I have. Okay, very good. So then we basically have to, well, what we want to do is to solve the self-consistency equation. And then you could also do some sort of singular perturbation theory at the level of this kind of algebraic or transcendental equation. But what we actually do is to sort of compare between the self-consistency equation for the unhomogenized and the homogenized problem. And in fact, in the case where you have this kind of non-separable fluctuations, it's easy to prove using properties of periodic functions that it is indeed the case that the limits do not commute. Okay, so even if I actually send epsilon to 0, so I'm not in this situation where I take epsilon to be small but finite. If I have non-separable fluctuations, so if I am in this case, the two limiting bifurcation diagrams are actually different. And yeah, as I mentioned earlier, so we kind of know how to do all these things kind of properly if we first send epsilon to 0 and then n to infinity in the opposite limit. I can tell you after the talk what it is that we have been trying. And of course, the natural question is, why is it that you don't combine epsilon and n? And again, I can tell you a bit about this and sort of what the right distinguished limit should be for this problem. Yeah, so then we can actually compute the free energy at equilibrium because we have this nice formula. Of course, this is the standard formula, like if you like, from finite dimensional interacting diffusions. And then we have this additional term that we obtain in the mean field limit. And you can sort of play this game and look at all sorts of different potentials. So you have the sort of, I don't know whether I should call this a nucleation, but you have all this kind of the emergence of new branches and so on. Now, one can prove that for this model only exhibits continuous phase transitions. Okay, so there are no discontinuous phase transitions. So if you calculate the free energy of the different branches and so on, you will still see that this additional sort of branches do not correspond to minimizers. To the minimizer of the free energy. And then you have a situation like this, where basically, so for the unperturbed problem, you have no phase transitions, and then you have the emergence of all these branches. And you can confirm these results by doing particle simulations and also by solving the evolution Fokker-Planck equation or Makin-Vlasov equation. So this is the simulation for just taking a quadratic potential and perturbing it by cosine of x over epsilon. For the if I don't homogenize the dynamics, so then I end up with a distribution that is actually multimodal. Okay, so which would sort of, it's in accordance, if you like, with the fact that if I keep epsilon small but finite, then I expect to have more than one invariant measures. Whereas if I solve the SDs for the homogenized dynamics, then I end up with a Gaussian distribution. Okay, and I can also do this by solving the evolution PD. And again, I have this kind of difference that whether I have a multimodal distribution or a unimodal distribution depends on the order with which I choose to take the limits. Now, I presented these results for the case where we have a periodic, locally periodic potential, because in this case you can also do some analysis. But in principle, you could also sort of go through the same exercise for, say, random potentials or non-periodic multi-well potentials. So Zofia, in her thesis, she used this very nice rational potential, and then you can think of a variant of this where you sort of randomize the position of the minima and their depth and so on. So then you can generate potentials that look like this, and then you solve the self-consistency equation, and you can get bifurcation diagrams of this form. Okay. Right. So now let me move on to the second part of the talk. Are there any questions? Okay. So where we look at the Makin-Vlasov equation on the torus. So rather than having a confining potential, then I sort of put everything in a box. So, well, this is my confining potential. And I consider the dynamics with periodic boundary conditions. Okay. You can, in principle, also, derive this as the mean field limit of a system of interacting agents like this Kuramoto model that I showed, or models for opinion formation. Though one has to be a bit careful with the boundary conditions, but again, we can discuss about this. Right. So now I want to do exactly the same for this model. I want to check whether we have phase transitions and to characterize them. And in fact, for this model, we can have both continuous and discontinuous phase transitions. So let's see if this works. I will be actually extremely pleased if it works. Yeah, let's see. Yeah, OK. So if I have this noisy Kuramoto model, then this is sort of the nature of the phase transition, if you like. So I can either have no phase locking, which is for the case where the interactions are sufficiently weak, or I can have phase locking, which means that I have sort of a uniform distribution. And OK, so let's see if yeah. So we want to classify continuous and discontinuous phase transitions for this model. We want to get a better understanding of the free energy landscape. And what is actually really interesting, I think, in this problem is that it exhibits this kind of very strong kind of dynamical metastability phenomenon. So there is, like for example, for these models for opinion formation, if you are at sufficiently low temperatures, you have the formation of clusters that then the clusters interact, and in the end, you might end up into some sort of droplet formation or consensus formation. Let me show you, again, if I get this to work, an example where, so I solve the equation in 2 dimensions, and this is for some variant of this bounded confidence model. And well, maybe I should run it again. So what so I start with a uniform distribution, if you like, which would correspond to not having achieved any kind of consensus. Then if I choose the parameters the right way, I end up with sort of the formation of a cluster at the origin. OK, so again, I can tell you what we are trying to do in order to understand this sort of phenomena, but yeah.
That was on a periodic box, so what's causing it to choose the center? It keeps choosing the center. Are you shifting with the center map?
I think it's just, I mean, for the particular potential that we consider here has too many symmetries, so I don't think it's kind of sort of essential feature, if you like, of dynamics. What is interesting is that you have this kind of sorry. Sorry. OK, so let's continue. Right. So right. So this is the most interesting part that I won't really talk about. But let's see. Right. So if I mean, we know that if the potential is the interaction potential is H stable, which means that all of its Fourier modes are positive, then there are no phase transitions, and it's actually quite easy to show this. And this is, of course, has been known for a long time. So now I will decompose my potential into the H stable and the H unstable part, so the positive Fourier modes and what's left. And the sort of nature of phase transitions and their existence or not depends on the part that is in the orthogonal complement, if you like, of the
unpack what that H-stable definition means?
It says that you have positive Fourier modes. So if you write the Fourier transform of the interaction potential, it has only positive Fourier modes. So if you have only positive Fourier modes, this would correspond to the case of convexity, if you like. And you can show that the uniform distribution is always the unique stable stationary state. Okay. In addition, in sort of a difference between the previous model and the one, okay, I shouldn't try my luck. And the one that I presented here is that okay, so yeah, so for the model on the torus, it's always the case that the uniform distribution is a stationary state. Okay, so whether you have phase transitions or not depends on whether the uniform distribution is the unique stationary state and whether it's stable or not, when it loses its linear stability, and so on and so forth. Okay, so I have the same kind of nice sort of gradient structure that I had for the previous problem. Now I don't have the internal energy because I don't have a confining potential, but I have I can decompose my free energy into the entropic part and the interaction energy part, and now I'm using kappa to denote the strength of the interaction as opposed to theta. Now in the previous in the first part of the talk, I could characterize the number of phase transitions, or I mean, I could sort of calculate the number of stationary states that I had by solving a nonlinear algebraic type equation or transcendental type equation. It's no longer true here. So I can still rewrite the stationary Fokker-Planck equation as an integral equation, but it's still an infinite dimensional object, if you like. So it's not clear whether I can kind of parameterize the equation here so that I end up with a finite dimensional system of self-consistency equation. Now, I can, in some sense, almost do this because just like I derived the self-consistency equation by requiring that the first moment is indeed equal to the first moment, I can expand the solution here in a Fourier series, and then I can expand the integral equation, the integral operator here, into a Fourier series, and then I obtain a sequence of self-consistency equations for all the Fourier coefficients. Okay, so there is, and in fact, for the Kuramoto model, this is exactly what we can do, and we obtain a self-consistency equation for the first non-zero Fourier mode. Right, so then if I want to characterize stationary states, I either solve the stationary Fokker-Planck equation, I look at minimizers of the free energy, or I look at critical points of this integral equation. I always have the case that the stationary state is sort of the uniform distribution of the stationary state. And I can easily show, first, I mean, we can easily prove existence, uniqueness of solutions, and so on for this kind of dynamics. We can show that in the case where we have an 8 stable potential, then we have exponential stability in relative entropy, or in weighted L2 spaces. And in the case where the potential is not 8 stable, then of course this is a conditional result on the strength of the interaction. Okay, so now if I go back to the cosine potential, what I refer to as the noisy Kuramoto oscillator, I can quite easily actually solve this integral equation by expanding everything in a Fourier series. And the self-consistency equation that I get for the first non-zero Fourier mode is basically the same to the one that, I mean, has the same convexity and so on, to the one that I present in the first part of the talk. And in fact, is sort of the same thing that we get in the Ising model, right, in the two-dimensional Ising model. So I can easily then prove that for this particular example, I have the same kind of piece-Fourier bifurcation. And I can also obtain one-cluster solutions and even multi-cluster solutions. So the transition between like the uniform state and a localized state would correspond to going from a uniform state to something that looks like a cluster. Okay, so then using Crandall-Rabinovich theory, we can obtain a local bifurcation result. In particular, we can find conditions on the Fourier coefficients of the interaction potential so that we do have bifurcations, and in fact, we can characterize the critical strength. So in the first part of the talk, I gave a formula for the critical temperature in terms of the strength of the interaction and the inverse temperature. So we can do something similar here for the critical strength of the interaction. Right, and then some examples. So I still have the, I mean, I can use this general theorem in order to, again, check that for the Kuramoto model, so for the cosine potential, I get the right sort of critical value for the strength of the interaction. If I have a quadratic potential, I can again compute what the critical interaction strength is. And then I can cook up examples where, in fact, I have infinitely many bifurcation points. So I'll have infinitely many solutions to this equation. Okay. Right. Okay. So now I should mention like a sort of a remark on the literature. So there is a couple of papers by Tamura from the 80s where he actually used the sort of Crandall-Rabinovich theory in order to prove that you have bifurcations in models of this type. But he made the assumption that the interaction potential is actually antisymmetric as opposed to symmetric. This simplifies the analysis a lot because like the null space of this compact operator that you need to check becomes one-dimensional in this case. I thought, it's kind of interesting. If you're a pure mathematician, you think it's fine to have an interaction potential that is actually antisymmetric when sense temperatures. Anyway, but so if we modify this analysis and we sort of, for the class of potentials that we consider in this problem, so then we get this local bifurcation result. And in fact, we can say a bit more. So there is a nice paper by Chase and Panfaro from 2010 where they give this concept of a transition point. Because now I can do several different things in some sense, right? So I can do linear stability analysis, which is basically what I presented, but I can also think in terms of like global minimizers of the free energy functional. So I define then a transition point kappa c to be one for which for all. So again, remember this is the strength of the interaction, or if you like the inverse temperature, I mean, you can play with one or the other. So for all interaction strengths below this, I have that the uniform distribution, so rho infinity denotes the uniform distribution, is the unique minimizer of the free energy functional at the critical point, at the critical interaction strength. The uniform distribution is one possible minimizer of the free energy functional. And for all interaction strengths greater than the critical value, then there exist other minimizers which are not the uniform distribution. Okay, so then once I have a continuous, once I have the definition of a transition point, then I can distinguish between continuous and discontinuous transition points and the corresponding phase transitions. So if I have this kind of continuity property, then of course I will talk about a continuous transition point. If I don't, I will refer to it as a discontinuous transition point. And there is a connection between the transition point and the point where the uniform distribution loses its linear stability. But they're not necessarily the same. In fact, whether I have continuous or discontinuous phase transitions depends quite crucially on this point. So the result then, well, of course, again, this is a problem that has been studied quite extensively. And there is, we can, so again, that we have a transition, I mean, we can have phase transitions only if the potential is not H stable. We can study properties of the minimizers of the free energy functional. And based on this information, we can actually characterize continuous and discontinuous phase transitions for this kind of dynamics, so Makin-Vlasov dynamics on the torus, depending on one hand the sort of properties of well, the uniform distribution losing its linear stability and so on, but also by introducing an appropriate resonance condition. So I'm presenting this kind of results now in one dimension because it's much easier to write them, but many of these results are actually also valid in arbitrary dimensions, finite dimensions in space. Okay, so it's not necessarily to look at the Makin-Vlasov equation in one dimension in space. You can also look at it in on the d-dimensional torus. Okay, so then this is sort of the main result in connection to continuous and discontinuous transitions. So we have basically this kind of duality. So if we have this kind of resonance condition, then so assuming that we have a transition point, so then if this resonance condition is satisfied, then this is actually a discontinuous transition point. And if I actually kind of shift the spectrum a bit, so there is a condition on the spectral gap of the linearized operator that, again, maybe I shouldn't get into. Then I can show that, in fact, the transition point is continuous. Okay, so I think I should stop here.